Hello everyone, this is Vasishta from aerobie section. Today I am going to explain about fluid viscosity in fluid dynamics. So, fluid viscosity. What is a viscosity? Viscosity is a resistance of a liquid to change in shape or a movement of a neighboring portions relative to one another. Viscosity denotes opposition to flow. The reciprocal of the viscosity is called the fluidity. A measure of ease of a flow, molasses, for example, has a greater viscosity than water because part of a fluid that is forced to move carries along to some extent adjacent parts. Viscosity may be thought of as internal friction between the molecules. Such friction opposes the development of velocity differences within a fluid. Viscosity is a major factor in determining the forces that must be overcome when fluids are used in lubrication and transported in pipelines. It controls the liquid flow in such processes as spraying, injection molding, and surface coating. So, we have some measurements on how to measure the viscosity using calibrate viscometers. It gives the kinematic viscosity of a fluid. It is based on Poisson's law of steady viscous flow in pipe. The formula is mu is equal to pi r power 4 GLT by 8 LV is equal to K into T2 minus T1, where mu is the kinematic viscosity and R is the capillary radius, L is the mean hydrostatic head, and G is earth acceleration, L is capillary length, and V is the flow volume of a fluid, and T is the flow time through the capillary, where K is the capillary constant which has determined experimentally by applying a reference fluid with a known viscosity. Example, by applying freshly distilled water, the capillary constant is usually given by the manufacturer of a viscometer. Fluid viscosity. The fluid viscosity sometimes referred to a dynamic viscosity or absolute viscosity. It's a fluid resistant to flow which is caused by shearing stress within a fluid and between a flowing fluid and its container. Viscosity is usually denoted by the Greek symbol mu, and it is defined as the ratio of shearing stress tau to the rate of change of velocity v, which in mathematical terms can be expressed as dv by dy. The derivative dv by dy is called the velocity gradient. That results in the important equation for fluid shear for viscous or laminar flow. Tau is equal to mu into dv by dy. The result in the important equation for fluid shear for viscous or laminar flow, tau is equal to mu into dv by dy. However, the above equation is not applicable for turbulent flow where a large amount of shear stress is due to the change of a momentum between adjacent layer of a fluid. To determine whether the flow is laminar or turbulent requires that you calculate the Reynolds number of a flowing fluid. Laminar flow will occur when the Reynolds number is less than 2300. From the above equation, it can be determined that the dimensions of viscosity are force multiplied by time divided by length square, or FL by Ft by L square. The units of viscosity in English systems and the SI systems are lb into second per feet square or slug feet second, and Newton square meter square or kg meter square. Dynamic viscosity. The Pascal unit is specifies pressure or shear stress or force per area. Pascals can be combined with the time to define dynamic viscosity. Mu is equal to Pa into S, and 1 bar of Pascal is equal to 10 poise, that is 100,000 centipoise. Centipoise is commonly used to describe dynamic viscosity because water at a temperature of 20 degrees Celsius has viscosity of 1.002 centipoise. The dimensions of dynamic viscosity are force into time divided by area. The units of viscosity accordingly is Newton second per square meter. which is usually expressed as Pascal second in SI units. The viscosity of a liquid decreases rapidly with an increase in temperature, and the viscosity of a gases increases with an increase in temperature. Thus, upon heating, liquids flow more easily, whereas gases flow more sluggishly. For example, the viscosity of a water 27 degrees Celsius is and 77 degrees Celsius are 0.85 into 10 power minus 3 and 0.36 into 10 power minus 6 Pascal second respectively, but those of air at the same temperature 1.8 into 10 power minus 5 and 2.08 into 10 power minus 5 Pascal second. For many fluids, the tangential or shearing stress that causes flow is directionally proportional to the rate of a shear strain or rate of deformation. The results, in other words, the shear stress divided by the rate of shear strain is constant for a given fluid at a fixed temperature. This constant is called dynamic or absolute viscosity, and often simply the viscosity fluid that behave in this way are called Newtonian fluid in honor of Sir Isaac Newton, who first formulated this mathematical description of viscosity. So, coming to know about kinematic viscosity. Viscosity can be measured by timing the flow of a known volume of a fluid from viscosity measuring cup. The timings can be used in formula to estimate the kinematic viscosity value of the fluid in centistokes. The motive force during driving the fluid out of the cup is the head of a fluid, which is also contained with the equation that makes up the volume of the fluid. When the equations are rationalized, the fluid head term is eliminated, leaving the units of a kinematic viscosity as area by time. The motive force driving the fluid out of a cup is head fluid, which is also contained within the equation that makes up the volume of a fluid. When the equations are rationalized, the fluid head term is eliminated, leaving the units of kinematic viscosity. V is equal to meter square per second. 1 meter square is equal to 1000 strokes, that is equal to 10,000 centistrokes. Water at temperature at 20 degrees Celsius has a viscosity of 1.004 into 10 power minus 6 meters square per second. This evaluates to 1.004400 centistrokes. This value must be converted back into 1.00 into 10 power minus 6 meters square per second for using calculation. The kinematic viscosity can also be determined by dividing the dynamic viscosity of a fluid density. Kinematic viscosity of a fluid density with a For some applications, the kinematic viscosity is more useful than the absolute or dynamic viscosity. Kinematic viscosity is the absolute viscosity of a fluid divided in the mass density. The dimensions of a kinematic viscosity can be determined. The dimensions of kinematic viscosity are area divided by time. The approximate units are meter square per second. The units of a kinematic viscosity of a centigram gram in a CGS system called the Stokes in a Britannian, the Stoke in the US. Is named for the British physicist Sir George Gabriel Stokes. The Stoke is defined as 1 centimeter square per second. Applications. So, the viscosity applications can be seen in our daily life. The selection of lubricant for various purposes. We can choose an optimum range of viscosity for engine oils, for high loads, and also for speed operating high viscous lubricants is required. For example, if we want to run an F1 Formula 1 race car, we need high viscous engine oil so that the engine can take the extra power from the fluids. In pumping operations, for high viscous fluid, high power will require. For low viscous fluid, low power required. As we can see in an example, if we pour water from a high surface to low surface, it comes fast because it moves fast from upper surface to down surface because it has a lower viscosity. If we take honey for example, it will not move with the same speed of water from above to the ground. In making of fuels, for making blending fuels also we need less viscous fuels are easy to mix. If we mix, we can mix anything in water because it has less viscosity. If we want to mix it in another any type of liquids, it will not. If we want to mix honey with the paint, it will not. It will take more time because they are more viscous in the operation of coating and paint printing. Printing and coating process also include the high viscous liquids. So this is all explanation about a fluid viscosity and types of viscosity and its applications. Thank you.